All right. Hey everyone. Welcome to Advanced Track. Today we're going to be talking about neural networks, standard stochastic gradient descent, and CNNs. So, the host has asked you to start.
Yes.
Yeah. Okay. There we go. Okay. All right. Just technical things. It's been a bit of just things going on. All right. So.
Just quickly hide it so people don't. There we go.
Yeah, I got you. All right. All right. So, who are we? Hey, so I'm Wade. I'm a fourth year math econ major.
Hi, I'm Sparsh. I'm a second year Ling and CS major.
Hello, I'm Yu. I'm a third year computer science major.
All right. And you got okay, I guess. All right. All right, so to give an overview of what we're going to go over today, we're going to start with optimization and gradient descent, and then we're going to talk about a couple other types of gradient descent that are used in neural networks, and we're going to talk about neural networks and forward propagation, and then we're going to talk about a special type of neural network called the CNN, and then also convolutions, and then finally we're going to end with a note on ethics.
And before we start, let's give it up for Sparsh for wearing the lobster costume for your viewing pleasure. Woo!
All right. Yeah, so with that out of the way, let's start by talking about optimizers. So how does the question is, how do you tell a model about its incompetence? Or more accurately, how does a computer know how well a model is doing? You might think maybe you can tell right or wrong, but really what we want is that this is just a generalization is loss or the objective or residual. So basically an error, and the smaller the error, the better. And so optimizers work by trying to lower a model's loss by modeling or by nudging the weights each. And it does this again and again and again. Hopefully we get to a good point where the loss is low enough to where it generally gets most of the predictions correct. So the thing is, a lot of these modern neural networks, they operate in several thousand dimensions, which, I mean, if you can't see it, that's on you. I'm just okay. Yeah, but it's on all of us. So we're going to think about this with just two weights. So we have W1 and W2, which is
that even feels a little bit abstract. Do you think about the really simple model of a linear line, AX plus B? We are like seeing or part of AX plus B approach. Yeah. So imagine we have a model where those are two parameters, A and B, and your input will, in this case, be X.
Yep. Yeah. So, and then we have a loss function, which is a function of the two weights. And so we can plot F as a loss landscape. So if you've ever done a sort of 3D graph before, used like one of those, even if you've done 2D, if you've thought about, like Desmos or whatever, I'm sure many of us have used that kind of thing. You can basically visualize it like so. And then the goal is to find the point that's a global or a good local minimum for this loss. Obviously, as we said earlier, it's not limited to 2 dimensions. Models can have an ungodly number of weights, which obviously we can't really visualize, but just by looking at 1 or maybe 2 dimensions, we can sort of get an idea of what's going on here.
Yeah, and to kind of concretize this a little bit more, specifically here, W1 and W2, we're thinking of it as it is a representation of our model. And the loss landscape represents all the possible ways our models can be in these sort of combination of W1 and W2. Think of W1 as one of the horizontal axis, and W2 as the other horizontal axis, and our height here is our loss. So the loss landscape essentially represents all the possible values, all the possible states, all the possible ways that our models can be. And each state of our model corresponds to what its loss would be if we say test the model on our data sets. And that's what a loss landscape is. And you can kind of see how we want to get to, if we can get to a global minimum, and it's a really good local minimum. aka what is the combination of W1 and W2, aka our weights, such that we are minimizing the loss of the model or maximizing its modes.
And just to like piggyback off that point real quick, another analogy that you could use is like if you were to say walk around the room, for instance, where the x and y coordinates of the room like describe where you are in the room. Then if you say take a step up in that direction, then your height in the room will increase going up. So the idea is that you want to sort of find the lowest point by like walking around your landscape, which means like varying your parameters as much as possible, so that what you end up with is the lowest possible loss for the model. And we'll sort of make it more concrete what the loss is in a little bit.
So how do we actually, so with a linear model, it's pretty simple to just, it's generally much, with one weight, it's pretty easy to just look at a graph and see where the minimum local minimum is. However, in a large number of dimensions, this becomes really complicated really fast. So we need a way to iteratively descend down the loss landscape. And we do that with gradient descent. An analogy for this, if we go back to the loss landscape here, say instead it's a mountain range. So we're thinking 2D here. And what you want to do is you want to get down. You want to get down to the lowest point. But you don't necessarily follow a trail. You want to follow the fastest way down. And so that's what we do with gradient descent. So what gradient descent does is we, first of all, how many of you have heard of gradients before? Okay, good. So yeah, basically it's just a vector with the derivatives with respect to each dimension. And then, and so that vector represents the direction where basically it's, how much it's changing with respect to, basically the maximum.
The direction of steepest descent.
Yeah. Sorry, I couldn't quite get the words right. Yeah. Basically, if we maximize so that's the gradient ascent. But what we want is descent. And so what do? You just go the opposite way. And so you just use the negative. So G is the direction of gradient ascent, and we use negative G like so. And so we calculate, so PyTorch actually calculates this gradient for us with a technique called back propagation. And we'll talk more about that in a future workshop. So the gradient update rule is given by the next iteration equals the current iteration minus the learning rate times our gradient. So as I alluded to earlier, we're taking a walk down the loss landscape hill. And so that tells us what direction all the weights and biases should change. And then we make these tiny adjustments in those directions. And then hopefully we get a lower loss on the next iteration, and so on and so forth. So so one thing to note is we don't want a learning rate that's too high, but we also don't want one that's too low. If you pick one that's too low, you're going to be walking down that hill forever. If you go too fast, you could wind up overshooting the minimum and you could actually end up with a worse loss. So it's important that we choose the right learning rate, and as we'll see, and we'll talk more about that in a second. But first, here's a little simulation made by ACM Hack. And so this is, if you want to, they can see the slides right on the.
Yeah.
Okay. Yeah. So if you want to go to the slides, you can play.
The slides are right here. Bit.ly ACM F23 advanced cluster. If you want to see the slides and play with the simulation yourself, and do it over there. We're not gonna open it just because of time. We started late already. Yeah. We had technical problems, unfortunately. Yeah, we don't really have time, but I highly encourage you guys to play around with this. You'll be able to see you can overshoot if you go too big, and it's just going to take forever if you go too small. So yeah, and then there are also various other challenges with different types of gradient descent, which we'll
talk about in a second. So atom and momentum are variants that overcome convergence problems. Hello. All right, so now we're going to talk about a couple different types of gradient descent. So there are a couple decisions we need to make. We could check 1 point at a time. The problem with this is that it's essentially a gamble. We could get really lucky and just land right in the valley, or we could just get in this like really high hilly area where it's really hard to get down. So one input is really unstable. So it's just luck at that point. To be fair, machine learning is a lot of luck, but we're basically going all in on this one point we're doing, and that's not what we want to do for a reliable model.
Oh, and one quick thing, just to contextualize this, when we say how much training data we feed in at once, it's gonna be like, how's training data involved in this, right? Because like what we were looking at before, it seems like the neural network is a function of our weights. Why does the training data matter? So what we're actually doing is we have these weights in our neural network model, and we're saying we have this data set. When we run this data set through a neural network model, we get a loss for every single one of these data sets. And typically what we do is say the average loss, right? And what's happening is we're using this loss information to then calculate our gradient with respect to our model weights. And then the question becomes, well, how much data do we feed in at once? Do we feed in the entire data set with just one data point, some of the data points? And that's what we're trying to answer here. And this is where terms such as mini-batch gradient descent and stochastic gradient descent, which something you may have heard of, comes in. In this case, with one input, you can kind of see how gradient descent becomes unstable, because if you have, say, a really weird-looking cat, a cat that really looks like a dog, or some other outliers in your data, that may mess up your gradients. Even if you have a low learning rate, it makes the process of going around really stochastic and really sporadic. And that's not good. This also has another name called stochastic gradient descent. It's stochastic because we're randomly choosing data points to put in to randomly choosing data points to compute our gradients. Stochastic, for those of you who don't know, is random.
Yes. So what about? Oh, sorry.
Why do you gradient descent rather than just like find the derivative and come up with that route?
Oh, so that's actually a really good question, because like for most functions that you like take local minima, right? We just like set the derivative to 0 and we find it. But the problem is we don't know what the function is that's generating our loss landscape graph. Right? It could be some super arbitrary function. Like if we go back to the slide where we were like showing that like 20,000 dimensional space or whatever, like that looks really weird, right? Like it's like not a function that we know, because if we knew the function, then we could just like take the derivative and just find it. But we don't know what the function is that's generating this loss. We just like sort of blindly wander around the landscape until we find like the local.
Mm-hmm. Another thing is the gradients, strictly speaking, is a local view, right? If you think about it, when we're calculating the gradients for any 2D graph, for example, if we have something like this, right? The gradient at this point is very flat. But if we just literally move down a little bit, the gradient suddenly becomes very steep. The gradient is a local view of the graph, and that's why we have the learning rate over there. Because we're making the assumption, or we know that, especially with something as complex as neural network, the gradient at a local point does not represent what it's going to look like on a global scale. That's why we're more careful, more conservative, more, like we don't move nearly as much every time. That's why we have the learning rate there. Typically something really low, like 0.1 or 0.001, to dampen this process and to kind of make sure we don't just, again, if we have, a really big, decrease here, we don't want to, and we have a really big gradient, we don't want to just overshoot and go all the way here, right? It's much better to slowly descend all the way to the bottom versus kind of ping-ponging back and forth all the way until we reach the bottom in a simplified case. Does that make sense? Yeah.
Yeah. So going back to, there's another question. What if we just feed all the data in all at once? Obviously, so if we had infinite compute power, sure, it might work pretty well. Unfortunately, that's just not how it works. So basically, if we pass in all the data in the current form, we take the average of all those gradients, it becomes way too much for our computers. To give you guys an idea, I think I don't even remember how much it is, but like to train like ChatGPT, I think it was worth like hundreds of millions of dollars or something crazy like that.
And even the little demo, like the little model that we'll be eventually be building, the classification model, we're going to be working with 60,000 data points, right? That's a lot of data points. And even with like Google Colab and like large GPUs, that batch size is still a little bit too big. That amount of data you get in at once is still too big for most of our computers.
Yeah, it's just too much. So if you want to blow up your computer, go ahead and do it. But if you don't want to do that, which I hope you guys don't want to do that. We don't want to pass in all the data at once. So what do? We pass in some of the data with mini batch gradient descent. So we pass in some of the inputs, and then we take the average of all those gradients, and we use that average gradient to update our model. So we might pick, so for example, on a data set with 60,000 or so some odd images, we might pick a batch size of 64 or 128. So we pick 64 images each time, and then we pass those in, and we take the average of each of those gradients, and we use that to update our model.
And kind of to clarify why exactly we're doing this, if you go back to one slide, this is kind of like the ideal. We kind of want to pass in all the data because to us, it is the best approximation of the gradient, at least at this focal point. However, we can't do that. So we're using a small batch of the entire data set to hope that would be a good enough approximation of the gradients over time. And there are other methods with our optimizers where we can say take a moving average of the gradients and stuff like that, which we'll cover in future workshops, that you can basically try to, even though you're taking a small batch size, it is a good enough approximation of our gradients. And especially when combined with other optimizer methods, we can kind of almost steer our gradients in the right direction. And eventually, with a bunch of iterations and also a low enough learning rates, we can kind of hope that this, even though this process is kind of stochastic, is going to get to where we would want to get to, if that makes sense. Right? Yes.
Are you meaning that we put data into different groups, by the groups, by the app, sort of like the average gradient each group and use them together? It's more like you take say you have 60,000 samples, you choose 64 of them, you pass them all into the model. The model is going to have a gradient for each one of those 64 samples. So you take those 64 gradients and you find their average, moving average, or whatever, and that's the gradient that you use to actually update the rest of the model.
Yeah.
And you do that 64 at a time until you get through the entire batch of 60,000 images, and that would be quite a deep talk where you go through all the images, and then you just keep doing that iteratively, 64 images.
Usually the process is you take in your data set images, you shovel it randomly, and you just say, all right, the first 64, second 64, third 64, and each of the 64s or each 128s, whatever your batch size is one iteration. And in every single iteration, you do the gradient calculation, average all the gradients, and you do this gradient descent. You nudge the model, if you will, and you start over again, and you can compute a new gradient with the new model that you just updated again and again and again until you get through the whole data set. If that's not good enough, you shovel again, start over.
Yep.
And also, just to clarify, we're talking about batch size of 64 and 128 and other powers of 2. That's not because powers of 2 are special, it's just a convention. Let's use this in the ML world.
Pretty much. Yeah. Any other questions so far? All right. Awesome. So to give a quick summary of all the terminology that we've used, because it's quite a lot of jargon that we've been throwing at you. So gradient descent is when we use all the data. Stochastic gradient descent is when we use one data point at a time. And then mini batch is when we use a batch, really, of data at a time. So 64, 128. And so if we
nowadays, a lot of these terms are becoming interchangeable because the reason why they were separate terms back in the days is because we were doing machine learning on really small models and with very few data points. So it actually mattered that we could feasibly pass in the whole data set and still call that a thing. We could just start with one data set because the model is simple enough. But nowadays, because we're usually working with really large models and deep learning, and we're working with a lot of data, whenever we say gradient descent, stochastic gradient descent, mini batch gradient descent, they're almost always referring to a gradient descent with a batch size, a gradient descent with a small batch. So we may use the term gradient descent here and there, stochastic gradient descent here and there, SGD, you may see that abbreviated a lot. Nowadays, we're almost always referring to gradient descent on the small batch of the data, and we're doing this iteratively. Does that make sense?
Mm-hmm.
Yes.
Yeah, that's, yeah. So, Yeah, and so as I alluded to earlier, the learning rate is something that we want to choose, but it's not something that's updated with each iteration. So it's not like the weights. So that's an example of a difference between a hyperparameter and a regular parameter. So a hyperparameter basically controls the training process of the model. So like the learning rate as well as the batch size are examples of hyperparameters. So, and these are not tuned, as I said, they're not changed during the training process. They're something that we set at the beginning, and then we use that throughout the training. So, the other example here is the architecture of your model, basically the type of model that you're using, whether it's a fully connected neural network, a CNN, an RNN, a transformer, whatever it may be. However, model weights, model biases, and training data are not hyperparameters. Model weights and biases, obviously, those are the things that we actually update during training. And so those are obviously not hyperparameters, they're parameters. And then training data, why is that not a...
Oh, because you don't control the training.
Oh, yeah, that's true. You don't.
If you control the training data, then like that's not the research because you're doctoring your results. That's generally transparent.
Yeah, that one.
Another way to think of this is hyperparameters are the things you decide, right? You may decide them based on, say, you train a model, you say, oh, that's not good enough. Based on this result, I'm going to try changing around the hyperparameter of the model, aka what defines the model and the training process, and see what happens if that would improve the results. Those are hyperparameters that you decide. That which then will still affect the model, but is usually something fundamental about the model itself or fundamental about how the model is learning.
Right. Yeah. So what we pass in is not a hyperparameter in that case. So, and now we're going to talk about training, validation, and testing data sets. That's you, right? Yeah. So now I'm going to hand it over to Sparsh in our lovely lobster costume and take it away.
Right. Okay. So far we've talked about generally how the model learns, like how it updates its parameters and whatever. So now we're going to talk more in depth about what exactly it does with the data sets that we provided. So for example, if we say have a bunch of handwritten digits in our data set and we want to train a model to look at that and then classify them into whatever number they are. See this as a 4, classified as a 4. So that would be sort of the end task that we're going to. And this particular data set is called MNIST because that's just what the data set is called. And we're going to sort of go more in depth into the details of what's going on there. Okay. Yeah. So first things first, we want to split our data up into 3 sections. The first section, the biggest section, is going to be the training data. And this is the data that you actually pass into the model and that it learns from. So when we talked about passing the data into the model, and then you get a loss, and then you use that loss to then calculate a gradient, which you then update all the weights and biases of the model with. This is the data that's being used for that. And the point of this is that the model takes this in and it sort of learns the trends and the patterns that are present in the training data. And hopefully these trends are reflective of the data at large. Next up, we have our testing data. And this testing data is also passed into the model. But rather than using the loss at the end to update our model and like fix it, this is just straight up just calculating accuracy, deciding is the output we're getting from the testing data the one that we want or not. And this is how we evaluate how good our model is. So in this case, we are doing forward, we're feeding the data forward through the model, but we are not updating the model and doing back propagation, which we'll talk about in a little bit as well. And then the third group is validation data. And this is the data that's used for deciding what the hyperparameters will be. So the reason that we want the validation to be different from the training data and the testing data is that we don't want the actual outcome of the model that we don't control to be affected by this. All we want is just to make sure that our model is functioning at whatever is the optimal setting for all the hyperparameters. So you want the learning rate to be just right. You want the basically the hyperparameters we discussed before. But you want those to be right. But it's not something that the model learns. It's just something that you control about the model. So you want to make those settings as good as they can be. Yeah. So you might ask, why would we do this in the first place, right? Why not just like have our data set, just pass it in, and then just decide how good our model is like by passing in the data set, right? And the reason for that is similar to the reason that ideally you wouldn't want to be studying like while you're taking your finals, right? Because your finals are supposed to reflect how well you know the material. And so for that, you don't want to just straight up do things that you've seen before. You want to do it on something that a model hasn't seen before to determine whether it can generalize from the training data out to trends in the real world and in the testing data, and also the validation data. Okay. So now that we talked about data sets, let's talk about the actual process of passing data forward through the model. So the basis of our neural networks is something called an artificial neuron. And this neuron is, you can think of like a layer of neurons in a network as just being like a list of numbers, like a vector. And so the neuron itself is just going to be a single number in this giant vector. So if you have, say, like a lot of times you might see like a graphic like this, where these circles represent neurons and contain values. You can also think of it as just a straight up vector like this, which is just a list of numbers. So you'll have like 1, 2, 5, 29, etc. And you'll just have those in a list. And those are your artificial neurons. And so what will happen is that you have one vector here, and then you want to multiply it by some weights. And those weights are then going to generate this second vector here. And then you multiply this by weights again, and you get here. Multiply this by weights, and you get to your final output there. And because these are vectors, when I say multiply by weights, you have to keep track of how each neuron relates to the next one, like to the next one and the one to the next layer. So this neuron connects to this one, and this one, and this one. So all three of these are going to have a say in what the value of this was. And likewise for this one, likewise for this one, likewise for this one. Yeah. So as you can see, if we take the previous layer, take those numbers, multiply its neurons by the appropriate weights, we can get the neurons for the next layer, like this. And then what we can also do is add a little constant. So that way we're not just restricted to just straight up just multiplying the numbers multiplying and adding the numbers in the previous layer. Yes?
Yeah, I have a question. So how does it know to like 4 different, like how does it know to multiply the weight class into 4 different sectors?
Oh, I'll get into that in the next slide, I believe. Okay. Yeah. There we go. Yeah, this is the answer to the question, how it knows to do that. So the idea is that you have a matrix that encodes all the weights. Yeah. So this matrix is going to explain how each number in the vector should be multiplied so that you can get the appropriate answer in the end. And has anyone here taken linear algebra? Okay, so the idea is that if you have, say, okay, this is like a little bit hard on the visibility, but yeah. Okay, so if you have like 2, 3, 4, 5, right? So these are the weights, right? So what you'll do is, if you have some output vector here, you'll do 2 times 1 plus 3 times 2 plus 4 times 5 plus 5 times 29. And that number that you get is going to give you this number up here, whatever it is. And likewise, we're going to have weights here. You multiply by these, and you get the second number in the output vector, and so on. And you just follow that same pattern again and again. And so that's like the details of the matrix vector multiplication. And you don't necessarily need to worry about it at that level. You just need to be concerned with the fact that you have a weight matrix, and you're multiplying a vector by that weight matrix to get the next vector in your model. Yeah, so that would be sort of what I just like talked about right here. Okay. So far, every single layer is a linear combination of the layer before. Does everyone here know what linearity is? Could you raise your hand if you know what linearity is? So the idea is that for linearity, you do some constant times your input plus a bias. And that is just a linear function, right? There's no square term in there, nothing like that. It's just a simple constant times your input plus a constant. That's it. But the thing is, if you take a linear function and then you apply another linear function to it, you're just going to get another constant times your input plus a bias. If you multiply it again, same way, you get the same thing. So the problem is, when you just keep applying linear transformations like this, you still end up with a simple linear transformation. So adding these extra layers is not actually making your model more complex, because you still just end up with constant times your input plus a bias. And that's not really helpful. So instead, what you want to do is you want to introduce nonlinearity. And you'll do this with what is called the activation function. And this nonlinearity is going to solve that problem, because now it's not so clear cut that you just have a weight times a constant plus a bias. Instead, you're going to have some sort of other weirdness going on. Like you might have a curve that's thrown in that changes how your output goes from one layer to the next. And so, yeah, as you can see, this term here is your nonlinearity function. So typically, like the prototypical nonlinearity function that we use is something called the sigmoid function. So the sigmoid function basically looks something like where this is x, y equals 1, and that's y equals 0. Something like that. Can everyone see it? Yeah. Okay. So that would be an example of a nonlinearity function, where we can see this is totally not linear because, well, I mean, obviously this is not a line, it's a curve. So that's the prototypical example. That's like, it's not used that much anymore because we have better ones. So one that works really well is called ReLU. And this is what ReLU looks like. It's just 0 until you get to 0, at which point it's just like y equals x. And you might think to yourself, well, this doesn't look very non-linear. I mean, it's just a line straight up. But the thing is, with this little making this a piecewise function like this introduces enough nonlinearity that we can actually get our models to work really well. And funnily enough, they actually work better with ReLU than they do with the sigmoid for reasons that are not properly understood. There are a lot of things about machine learning that just work because we found out they work, rather than, we work because they work because we fully understand what's going on.
One of the reasons why we have like a theory of like, hey, this is why ReLU works way better than sigmoid is because if you look at sigmoid, when you get to the edge of this function, it goes very flat, right? And when something becomes very flat, what does its gradient become? 0, right? And that's a big problem, because when we are calculating the gradients, we're using something called chain rule. Have you guys heard of chain rule? Yeah, right? Chain rule. We're just kind of multiplying derivatives all to each other. If we have a bunch of gradients that are below 1 and keep multiplying, the gradient vanishes. It's a problem called gradient vanishing, which again we'll talk more about when we get way deeper into graph propagation. But ReLU doesn't really have that problem. Yes, you have a gradient 0 when your value is negative, but your value is positive. Your gradients is just, well, your gradient. The gradient completely passes through as an identity. And because of that reason, we're not crushing the gradient in half the places. And just by doing that, it is enough for us to not lose gradients at the very, very, very deep models. Which is why nowadays, and when we eventually get to our code demos in future workshops, we will see, or like the larger code demos where we actually start building the model, a much more complex model. We'll see how we use ReLU instead of sigmoid or 10H, which is basically sigmoid, but like you've extended to negative 1.
Yeah.
That's the reason.
Yeah. And then there are also other nonlinearity functions as well. Like there's something called a softmax function, which will basically take in like your input vector, and then it's going to spit out a vector of probabilities. So it's going to say this is the probability of being in class 1, class 2, and so on. And you'll typically use this maybe as the output layer of your model if you're like doing a classification task. Or when we get to transformers, you'll see that we use softmax there as well. But generally, we'll use ReLU for most of the nonlinearity functions for our layers, but we might use softmax at the end for classification tasks. Okay. So now that we have our neural network, hopefully the structure is a little bit clearer. What's going on here when you see diagrams like this? You have your input layer, which is the list of numbers that are of interest to you. You multiply them by a weight matrix, add a bias, add a nonlinearity function, boom, you get your second layer. Do the same thing until you get your output layer. And then from there, you decide how good is the output of your output layer. And that's what we'll talk about next. So suppose we are trying to classify numbers from the MNIST data set, right? And our final outputs look something like this. So this is the probability of our number being 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So as you can see, most of these probabilities are 0, but the number corresponding to 2 and the number corresponding to 6 are somewhat high, which means that the model thinks that these are the 2 strongest possibilities for what the answer is. So that would be like, I don't know if you wrote something like that. Right, something like that. Or on the So this is the actual outcome of our model. And suppose that the number here is supposed to be a 6, right, in the MNIST data set. In that case, the expected thing that we wanted was that it's 100% going to be 6 and 0% is going to be anything else. And so this is what we actually got from our model. And this is, oh, hold on, you can't see the mouse. So this is what we actually got from our model, and that's what we expected to get from the model. So with this, we can calculate the loss. And there's a number of ways we can calculate the loss. One is the mean squared error, where basically you take the difference between what you got and what is expected, and you square it, and then you just add all those things up. And that gives you your mean squared loss. Then there's another thing called cross-entropy loss, which is a bit more complicated. But basically what it's a way of doing is it's a way of comparing probability distributions. So it's a way of comparing the probability distribution you got to the one you expected, and then seeing how close they are. And the closer they are, the better you do. The further apart they are, the higher the score, the worse you did. And that would be that is measured by something called entropy, which is like a measure of information. And that's, if you wanted to look more into that, it's related to a field called information theory. But basically, low probability events have a lot of information, and because they have a lot of information, you're going to have a high loss. And then there's another thing called maximum likelihood estimation. And this is a way of finding parameters to best fit your data set, given that you have some assumed distribution, which is the actual one that you expected. So basically what you're doing here is you're comparing this actual data that you have to a bunch of different theoretical distributions. And you're trying to see which one fits it the best. And that tells you what the sort of underlying probability distribution is versus the one that you actually want.
And just a quick thing. The reason why we use something called maximum likelihood estimation across entropy is because what we do, when the model outputs some sort of vector, that vector isn't limited to any rate, right? You can have a value of 100 on that vector. You can have a value of negative 50 on that vector. It doesn't matter. The question becomes, first, we got to convert that into a probability distribution, right? Some representation of the model thinks it is 30% true that this digit looks like a 7, 70% true that this digit looks like a 9, right? And we use this thing called softmax, which you may have heard us talk about before. But essentially what it does is it takes the output model, it puts that on an e to the power, so it just exponentiates it, and for each entry, it divides it by the sum of all the other exponentiated values. And because we're basically almost normalizing this output between 0 and 1, the values of every single other entry affects every single other entry. If, say, a single value is really, really high, it's going to push the other values to be lower, right? And because of that reason, when we do maximum likelihood estimation, what that's basically saying is, let's look at what the model predicted as the most possible thing. If that is indeed what the correct class is, then let's just say, I want that to be 1. When you're trying to push that to be 1, what you're doing is you're lowering all the other entries, right? Conversely, if you say, oh, that's actually the wrong entry, we want that to be 0. So when you're pushing down that entry, you're actually increasing all other entries. And by doing so, at some point, you're hoping that your model will get to the correct entry will be high, in which case then you can say, oh, that's the correct one. Let's make that higher. So that's kind of how our model was able to go from outputs to what we call loss function. And maximum likelihood estimation and cross entropy are actually two very, very similar things. Some machine learning courses use them kind of interchangeably. It's just small details that they're different, but that's the basic idea behind it. And that's how our model actually evaluates, hey, this is this error that the model calculates comes from this. The lower the score is means the more matching the two probability distributions are. Hence, the better our model is doing. Does that make sense? Okay, thumbs up all the way in the corner.
Yeah.
Any questions before we move on to what neural networks are, what they look like, etc.?
Okay.
Okay, cool.
So then real quick, before we move on to the next section, let's just review what we've covered so far so that you guys are fully prepped up for CNNs. So step one of any machine learning project, define your architecture. What do you want? How many neurons do you want in your first layer? How many neurons do you want in your second layer? And you just decide that. Number two, you initialize your weights and biases. And normally this is going to be done randomly. So you just like set them to random values at first. And then you trust that over time, the process of the gradient descent is going to nudge them into the right places. Number three, you feed your data in, as we discussed, through stochastic gradient descent. You pass in, say, 64 images. Each of those is going to have a loss. Then number six, you average out all of those losses. You use that to take the derivative of your loss function, which we covered just now. You take the derivative of that loss function with respect to all of the weights and all of the biases. That tells you the gradient. And you then use that gradient to then update all of the weights and biases by just a small step, which depends on the learning rate that you have. And then you just keep doing this again and again. And then eventually you're going to get to some point where your model has hit some kind of local minimum as far as the loss goes. And then to determine whether this is actually a good model, you finally pass it in the testing data and you determine if what you have is good or bad. So any questions about any part of this process? Yeah?
How do you determine like how to split the data in like testing, training, and evaluation? Like, is there a Python parameter that you can like tweak as well? Because like, I've heard like some people just do like 70, 20 instead.
Yeah, that's also just a convention. The 70, 20, 10 is, I think, the most normal split. And the reason is, of course, you want to have as much training data as possible to learn from. But you also do want to leave like stuff for the testing data, which would be the 20, and then 10 for just like fiddling around with the hyperparameters. But you can change that as you want to. Yeah.
When you have smaller data sets, you can switch it around.
Yeah.
So at one point, you can take one of the tests, you can study for the test automation training, you take another part, then shuffle it. And then each time you take the best, you can also, because of that, you get the best hyperparameter. You can get the average of the hyperparameter, get the best one to find it. Okay, that is great.
Yeah.
And in fact, in a lot of like machine learning competitions out there, especially the classification-based stuff, they won't give you the test data. They'll just say, here is a data set. Figure out what you want to do with it. And as a machine learning scientist, what you have to do is you will have to split it into your training data set in a very small part being your validation data sets. Do that a bunch of times, find the best type parameter. Then you say, okay, I think I found the best version of my model. Let's take the whole training data set, put into my model, and then they will give you testing data. You get predictions of that testing data, which you don't know if it's correct or not, and you just upload it to some website. And then eventually you'll announce the results by just looking at like the, say the 10,000 data points you predicted and say, are you correct? Because the whole point is we don't want people to be training their model, so it just happens to perform well on the testing data set. Because even though we're not training on the testing data sets, if we see the results of a testing data set, based on those results, we will make decisions about the model, which then will affect the model. So we are part of this pipeline of machine learning, right? Even though we're not directly training, we're still indirectly affecting the model if we're seeing the results of the model being evaluated on the testing set. And this is why, just like a final exam, we don't want to see how the model performs in the testing set until we're very sure that, hey, we're done with the model. We're done with training. Let's just see how this performs, and that's it. Does that make sense?
Yeah.
Yeah.
Does anyone else have any questions? Okay, perfect. If no one has any further questions, then I'll just give you guys some examples of architectures before handing it over to you for CNNs. Oh, wait. Whoops. Wrong architecture. My bad. So some types of architecture. We have the single layer perceptron. This would be a 2-neuron vector connected to your output vector, very simple. And then you have stuff called recurrent neural networks, RNNs. We're going to talk about those a couple weeks from now. LSTMs are a special kind of RNNs, but they address some problems that RNNs have, again, a couple weeks from now. And we have Hopfeld networks, both in machines, and stuff that we're going to focus on specifically are CNNs. We're going to start talking about that in a little bit and pick up on it next week as well. RNNs, again, a couple weeks. FFNs, we just talked about what feed-forward neural networks are. And GAN, which we're going to cover like way later in the quarter. So, do you guys want a small break? Okay. Yeah, we'll reconvene in 5 minutes. How does that sound? 5-10 minutes? Okay.
Okay, guys, we're about to. All right, guys, we're about to resume.
So now it's gonna introduce us to CNN. What powers most of computer vision and a lot of other things nowadays.
Yep. So, hello everyone. We're going to give you guys a brief introduction to CNN. You might be wondering, why are we explaining what CNNs are? And if you guys don't know, the long form is convolutional neural network. The reason that we're explaining is because today, in many state-of-the-art machine learning models, specifically computer vision, they're widely used. For example, a lot of surveillance algorithms use convolutional neural networks to sort of decompose an image and take the face and classify that face from others. So it's an extremely important neural network model that we use today. So what is it, right? It's essentially a very complicated machine neural network that has multiple different layers, right? One of the layers that it has is called a convolution, which is one of the most, which is the essential layer of this neural network. Essentially, what a convolution does is it takes an image, right, and it breaks it down through the different hierarchical structures that it has, right? So, you know, if I would ask you guys, for example, what type of structure does an image have? Let's say, for example, I have a data set of cats and dogs, right? How would I know the difference between a cat and a dog? I know this is kind of a dumb question, but how would you guys, like, if I could ask you guys? Yep, that's a good point. One in size, the size of the object that you're looking at. What's another one? Sound? You're getting there. You're getting there. It's close, you know. But I think if you see it in physical, yeah. Did you say tails?
I said nails.
Nails?
But tails too.
Yeah, that works, right? Nails. But I want you guys to think about the substructures. Like, for example, one sharp feature, like an ear, right? The curve of an ear, or the color of a cat. Specific cats have specific colors, or some of the spatial relationships that a cat has to another cat versus a dog to another dog, right? We essentially want to capture that spatial information and classify images using that spatial information. That's the key, right? We have a data set that has spatial information. We take that spatial information, we decompose it to a sort of conveyor belt structure, and then classify it. That's the big thing. That's the key that of what a convolutional neural network is. So benefits of a convolutional neural network. One big benefit is the sparse connectivity, right? So convolutional neural networks, as Sparse was talking about before, V4 neural networks, they have a bunch of different parameters, right? That's what you train in a neural network. And to train those parameters, it takes a lot of computational power, right? And convolutional neural networks sort of go against that by decreasing the amount of computation you need for an image, right? So can you guys sort of like give me an estimate of what you think a typical image has in terms of number of pixels? What do you guys think a typical image has in terms of number of pixels? Just give me an estimate, like a little bit of an estimate. Yep, I'm talking more in terms of size, the size of an image. How big do you think it is? Like the number of pixels an image has. I know this sort of seems like a lecture. I'm sorry, guys. I'm just trying to get. You're close, but we have to multiply it by a few orders of magnitude. Because suppose, for example, an image is 200 by 200 dimensions, right? Or 100 by 100 dimensions, right? Just that one channel, the RGB value, has 10,000 pixels. And if we multiply that 10,000 by 4, how many pixels do we have? Right? We have 40,000 pixels. Or if we have RGB, we have 30,000 pixels, right? Which is just incredibly dense. We don't need that type of data. There's a lot of noise in that data. We want to take out the hierarchical spatial structure of that data. And another key reason is parameter sharing, right? The same weight matrix, the same filter is applied to the whole image. So there's an interconnectedness of the parameters that affects it. Pretty drastic. So it's no longer sensitive to translation. So let's say, for example, I have a cat image. I love cats. And let's say the cat, like turns around in one angle and then turns around in another angle. Because we're taking the spatial information of that cat, that doesn't make any difference, right? And that's sort of the beauty of convolutional neural network is it doesn't matter how you translate the image, it can get that local substructure of that image. And that's why it works so well. So this is an example of an FNN trained on the MNIST. So I know Suarez explained what an MNIST is. It's basically a vision data set. And this is one example of the vision 8, right? The pixel size, the number of pixels in this image is around 784, 26 by 26 image. And we take this image, we take all the pixels for an FFNN, and we put it through the layers, right? We put it through all the hidden layers. Now suppose, suppose in this case we have a pixel size, pixel dimension of 784, and suppose we just have 10 nodes in the hidden layer, right? We would need 7,840 weights just to train this image for one layer. That's incredibly dense. It's just not feasible when you scale it up, right? We're dealing with hundreds of thousands of different weights, and it doesn't really make sense. But the beauty of convolutional neural networks is we only have these filters. Now we're not dealing with those weights anymore. We're dealing with different types of weights in terms of filter, right? So for example, in this case, we have a 5 by 5 filter, right? That's just 25 parameters. 25 is much better than a few thousand, right? So it's easily trainable and it's computationally efficient to train. So that's a CNN.
One slide more. I also want to motivate another thing is, so typically with, can you go back one slide? Typically with fully connected neural networks, what you're doing here to this image is, even though it's a 2D thing that we're looking at here, we usually flatten it. Like imagine you take this row, we put it there, we flatten this with one really long vector and we just feed it into a network, right? Now imagine you have this 8, I think this is an 8. But imagine you have this 8 over here, and I move it to this direction by just a few pixels. How will the inputs change? It will be drastically different, right? Like completely different, because suddenly this pixel here, it's like what place like 110 or something. You move it to here, it's like pixel 200 something, right? By moving the image around a little bit, it drastically changes the input. But to us, does the image change? Has the image changed much? No, right? So that's a big problem, because this dense connection is, it basically it assumes nothing about an input. It forgets that, hey, with images, things close to each other have meaning. The spatial location of our pixels have meaning. And that's what convolution allows us to do if you go to the next slide. Because it is a local operation, it looks at our image and kind of scans it locally. Even if you move the image around, the filter will eventually get to it, get to that pattern of pixels, which means convolutions make the assumption that we're more looking for patterns rather than some sort of really big global thing, at least for the first few layers. And because of that assumption, we're not only able to reduce our number of parameters, but secondly, most importantly, be able to adapt to images that are maybe slightly shifted a little bit. And that's very important in computer vision. Does that kind of make sense? Yeah. So that's kind of the motivation for CNNs, and you will see how CNNs or specifically convolutional layers are able to achieve this in a short bit.
So we're gonna dive into the structure of CNNs. So how CNNs work, how their layers are structured, and how the magic happens. So let's start with some of the layers of a CNN, right? So a CNN has like around 3 to 4 very key layers, right? The essential one is called a convolutional layer. That's probably the biggest idea that we would like to take away from the CNN. That's the essential feature there. And then another layer is called a pooling layer, right? And we'll also explain what that is, and that's pretty essential too. It helps in reducing the dimensionality of the image. So you have a 100 by 100 image, you can reduce it to an 80 by 80 image or 90 by 90 by image to reduce the amount of computation you have to make. One other layer that we have is called the fully connected layer. This essentially takes in that sort of broken down image and it classifies it, right? So you guys remember when I told you about the analogy of the conveyor belt? So you have an image and you break it down to the different edges, to the different colors, to the different properties of that image, and you put it through a fully connected layer. And the fully connected layer is what does the classification out. And it does this by assigning a probability to each potential output. And it says, okay, do we have a horse? Do we have a zebra? Do we have a dog? And then you just go from there and you take the one with the highest probability and then you predict. Is that clear? Does that make sense? All right. Let's start with the convolutional layer, right? So convolutional layer essentially takes in an input and it produces a dot product by taking the input and multiplying it by a kernel matrix. And it slides this kernel matrix across the image. It's sort of like you're sweeping the image and you're taking out every single thing that you don't want. And you might be thinking, why are we taking the dot product, right? Because the dot product, and it's clear by the name of the kernel. If you guys have taken linear algebra, you know what a kernel is, right? So I hope you guys have looked. Yeah. So essentially, the kernel zeroes out the aspects of the local image that you don't want, and it exemplifies the aspect of the local image that you do want. And so the image is transformed because of that. Let's give you guys an example of this operation. So you see, this is our image, right? And this is our kernel. And we take our image and then we slide it across. Sorry, we take our kernel and then we slide it across our image. And each time we take a dot product of the image in the kernel. Now, if you guys don't know what a dot product is, a dot product is essentially an element-wise multiplication of one vector to another, or in this case, one matrix to another, and we just add the values of that element-wise multiplication to that, right? So you see what's happening? It multiplies, and then it adds this up, and then that forms a new feature map. That's what we call the resulting output of a convolutional layer. We call it a feature map. So yeah, you guys have any questions on this? Because this is really important. Yeah.
Yeah. Where does the kernel come from again? Like, is this something that you said?
Yeah. So the kernel is essentially the trainable parameter. That's what we train in the neural network, right? It's this kernel. It's the thing that we sort of sweep the image across, and we sort of extract the important spatial features of the image. So that's all we train in the convolutional network.
And then we have like a bunch of these different kernels that all scan across the image and add up the results, and it's basically like a dense connection, but like on the kernel condition. But yeah, another thing I want to emphasize is why use the idea of a filter and why use the idea of a like pairwise multiplication and add it together. So imagine, say, you have a kernel and you're trying to find the eye, right? You're just trying to find the eye. Then, if you can set this kernel in a way such that the pixel values looks like it is, say, in the shape of an eye. Imagine the bright values of an image is positive, so like something like +1. And the dark values of the image is negative, like -1, for example. When, say, my eye matches up with the filter, which also contains an image of an eye, the bright areas match up. Okay, you have 1 times 1 is really big, right? And the dark areas, -1, matches with my eye's dark areas, -1, which multiplies together to get you 1 again, right? It's also really big. So when you add all these together, it becomes a really large value. However, if the filter is coming across, say, a flat wall, where it's just a bunch of zeros, or it's just a bunch of like really flat values, the really bright value multiplied with the not so bright value gives you an alright value. Then the really dark values in your filter multiplies with the alright value on the wall. It gives you a negative number. And when you add them together, they cancel out. So what the convolution filter is really saying is, here is roughly what my filter looks like. When I slide it across the image, or I slide it across the feature map, here are the spots. The brighter my final output is, here are the spots where this pattern has occurred in. Does that make sense? So that is why we have a filter, and that is why this kind of dragging feature is able to kind of like locate, oh, the eye is over here, heuristically. Okay. Any questions on that? Yes.
So is it kind of like the hidden layer, or is that separate?
So the hidden layer is something that we use to refer to, say, if you have just like one layer of the neural network, then the output of that layer is the hidden layer because we have more layers afterwards. And it's hidden because we're not seeing what's in there. Though recent research has shown that like we can do things to these hidden layers and we can come up with results. We can interpret what these hidden layers are to interpret what the network's actually doing. But it's hidden because like when you're running your model, you're not actually seeing what the outputs are. Yes.
I have a question about kernel. So like from the visualization, I can see like basically mapping the center of the kernel, like for the very first time you're mapping it to the corner of the initial image, and that creates the number for the corner in the output. So my question is like, if the kernel, the center of the kernel is aligned with the corner of the image, you don't have like all of the numbers. So how do you decide like what numbers go on like outside of the image so you can get the dot? So,
yeah, that's a really good question, and that's sort of a really important issue with convolutional neural networks sometimes, is they don't take into account the outer edges of the image.
We usually add with zeros, if you're wondering. Like, that's why we call it like zero padding. Because padding is a really important thing that you will see when you're defining convolutional layers.
Yeah, as Jonah said, we add it with zeros, then we increase the dimension of the data as we add it with zeros. So we can sort of get all the features that are at the edge. Because there might be some important features at the edge.
so basically you just like surround the images.
Yeah. And so there are other techniques you can use because this is sort of an important issue, but that's like most basic. Yeah.
Yes, another question.
And also, does the kernel output your or
No, it can be 5 by 5, it can be 7 by 7. The problem is when you increase the dimension of the kernel, the computation cost also increases sometimes.
Yeah.
In fact, sometimes, you guys remember the fully connected data I showed you at the end? We might not even use a fully connected data. We might use a kernel or like average pooling as a classification. So we can even have larger kernels. It's not needed.
Another thing is people back in the days did used to use larger kernels, and at some point people went, wait, 3 by 3 kernels works fine enough. That's gives us a much smaller model, it works about the same, why bother? And also we use odd number kernels, so like there is an obvious center pixel that we can center everything around. You can technically do even kernels, but the math becomes kind of annoying when you're implementing it. Or like when you're the machine learning engineer, you're like implement PyTorch, for example. But it's abstracted away from us, but it's just more mathematically annoying, which is why we stick with odd number kernels. There's only 1 by 1 kernels in very special cases, which we will cover next week. Yes.
Does the kernel always have to be like 3 by 3 and like 4 by 4? It can be like
No,
3 by 2.
Yes, that can definitely be the case. It's just again, people realize 3 is a really nice number. Why make it bigger when 3 by 3 is a good number in those cases? Yeah.
It's also when you reduce the dimensions make sense. You don't want a matrices that has like weird dimensions. You want a matrices that's even at that. So yeah.
That's the hyperparameter, which is something that you can set however you want.
Yeah. So the next slide. So now we're going to go to pooling layer, right? So a pooling layer is another essential layer of a CNN. Essentially, what it does is it takes a cluster of your pixel, and then it either averages it or it maxes. So you either take a max of that cluster or you take an average of that cluster, right? And what that essentially does is that reduces the image in terms of its dimension. So for example, you might have a 100 by 100 by 3 image. You can reduce that 100 by 100 by 3 image to 80 by 80 by 3 image with still relatively keeping the level of information that you want. Because a lot of the times images have a lot of noise. And you want to decrease that noise by taking the most important pixels from that local data and from that local information. And so these are the types of pooling we have. You can either choose global pooling or local pooling. In a lot of Google's models, we use global pooling on the final layer. So if you guys are interested in that, check that out. We can also use local pooling where we take local clusters. Once we do that, we either average the cluster or we max the cluster. That's what a pooling layer is. And this is a nice example of a pooling layer. So that's a max pooling. So for example, take the left-hand 2 by 2 matrix, 29, 15, 0, and 100. You just take the max of that value, that 100, right? I'm guessing that's pretty clear. And in this case, we take the average of that. Are there any questions for this? Yep.
Why is the maximum like a significant compared to the average?
That's a really good question. It's essentially, it matters what case you're using it by specifically. But for example, one case, if you want to extract a specific feature from an image, rather than taking the average of that image and taking in all the noise, you just want the most important pixel that's popping out of the image.
You remember like the explanation I was giving before, how like when the feature is there, the value is really high. When the feature is not there, the value is really low. A lot of times with CNNs, we care about what is there. We don't really care about what's not there, which is why we take the max form, because it directly allows us to extract, say, oh, this feature was in this rough location. Yeah.
And going back to your question, we'll have a demo and we'll show you guys why max is important. There's this, like in the demo, we explain pooling. And then finally, we have a feed forward layer. So as I was talking about the conveyor belt example, at the end of the conveyor belt, you have a feed-forward neural network that takes a flattened version of your tensor and it inputs it into the network, and it outputs a probability, right, through softmax function. And this probability tells you how likely that image is a certain classification. So, for example, you have a 0.95 chance that this is a dog, and it is a dog. So, in this case, the neural network was correct. It outputted the correct number. Yeah. So, do you guys have any questions on the feed forward layer? So I do want to say that this isn't always the case. We don't always use a feed-forward layer as that. We just use it so that it becomes easier to classify. But sometimes we can just take a global mean or a global average of the image and classify it that way. A lot of Google's models don't actually use feed-forward neural network at the end. They don't actually use it. So now let's get into some of the math. So let's talk about the math of a convolutional layer. Right? Suppose you have a W by H by D image. So width, height, and the number of dimensions, right? And then you have a kernel size K by K by D, which is the kernel. So you have a K by K kernel, and then you have D of these kernels, right? And you have P, which is the number of zero paddings you have around the image. So I remember someone asked about zero paddings. So P is the number. That's how many paddings you have in the image. Not in the image, but how much padding you add to the image. And then S is the stride length. So you guys remember before when I was saying that you sort of take the kernel and then you stride it through the image. This is how fast you do it. You can either do it slowly, one pixel at a time, or go really quickly, 2 pixels, 3 pixels at a time. And as you do this, you can see the division right here. You divide the image. So you dimensionally reduce the image. So for example, if you have a stride length of 2, then you have a 100 by 100 image, you're going to decrease it to a 50 by 50, right? Because you're taking half of the pixels and you're going along.
Another thing is, you may notice how, like, because if we're doing multiple pixels at once, that's a really effective way for us to also scale down the image, right? The thing on neural networks is we want to, at every single convolutional layer, we want to scale down the image, either via pooling, as you have seen before, or via the stride. Because what this allows us to do is as we scale down, we're still using the same filter size. This scaling down process allows us to look at a larger and larger area of the original image. We look at more global information. We're compressing the information, so we're extracting the most important features. And which is why you see stride and like this model of a neural network where it starts big and then it goes to be small and until we find some outputs. That's the reason why we're kind of having this sort of scaling down process.
And I wanted to explain one really important thing. So suppose you just have one kernel, for example, right? And you have an image that's 100 by 100 by 3, right? As you apply the kernel, what would you have? How would you sort of compress the data that you have between the channels? Because you have 3 channels, right? What we essentially do is we apply the kernel for each channel and then we just sum up the values for the RGB channels, right? And then that value is what we have here. So every single kernel maps to one feature map. But then you can have multiple kernels. You can have D number of kernels. You can have 64 kernels, 128 kernels, which is usually the case. And so you can have multiple output feature maps. And then some more math. This is the math for a padding layer. It's essentially the same thing. It's just the size of your output image, the WHG image, and you divide it by the stride length. So if you take it, if the stride length is 1, it doesn't affect it at all, and so on. So this is pretty clear. If you guys have any questions on the math at all, let us know. Yeah.
Does the feature map always have to have the same amount of leading ones to have the same kernel size for like basically each like pool?
Wait, can you repeat the question?
Kind of. So the kernel size is always 3, I'm assuming. So it always has to have 3 leading ones for each like image.
3 leading ones here?
Yeah, you always have to ensure that it has like 3 leading ones, so it has a kernel size of 3.
No, you don't always have to have.
Okay, so you can have like different kernel sizes when you're like looking at it.
Yeah, you can have different kernel sizes. Like you can have different like kernel sizes as you're looking at the image. Yeah, that's possible. Like you can have 3 by 3, 5 by 5, 7 by 7. Is that what you're asking?
Yeah. So you're just looking, but like if you're looking at the same image, okay, so you have like a different kernel size when you're analyzing each image.
Yep, that's really good. That's a really good question. You can have multiple different types of kernels, and it's a good thing because sometimes you want to reduce the image using different kernel sizes. So that's pretty important. So you can, yeah. Yep.
Are we manually setting the number that is unified to the kernel? Like the one on the platform that says one on zero. Are these numbers manually set or like it's wrong?
Or we say these numbers right here?
Yeah.
Yeah, so the kernel, so the values of the kernels aren't manually set. They're set, they're trainable parameters, right? So initially we randomize the kernel, and usually we randomize it based on a distribution, and there are different sorts of randomization for the parameters that affect performance. But you can just do a uniform randomization, and then that's how you get the initial parameters. And through training, gradient descent, you update the parameter. So you don't manually set it afterwards, only at first.
So at first we just write random -0 or -1.
Exactly. We just randomize it. And an important thing is when we randomize, we don't want the kernel values to be too big. We usually randomize it between 0 and 1, -1, -1 and 1, so that the values aren't too big for gradient descent.
Thank you very much.
Yeah. And some more math. So this is just an example of what a convolution is, like in signal processing. It's not as important, but it effectively gives you sort of like the mathematical overview of what it does. You essentially taking a function, you take another function, and you multiply that function at every step of that function by like a specific amount, and then you sum them, right? And that's by that area under curve. It is a mathematical interpretation and a connection to what a convolution is. And then, so we sort of want to go through this point, what formalizing different kinds of layers is in a neural network. So right now, as we go along, we're going to really start digging into what a layer is in a neural network, because that's specifically an abstraction of the neural network to make it easier to understand. Because if we're always talking in sort of weights and biases and so on, it's going to be really hard to explain what is actually happening in the neural network. So we abstract it to different layers. And that's how PyTorch works. That's how TensorFlow works and so on. We have different layers and we plug those layers in. It's actually like really simple stuff. You just plug those layers in and you have an optimizer and it does everything for you. So that's like the essence, right? And today we talked about convolutional pooling and fully connected layers. Yeah. So we're going to give you a quick demo right now. We're going a little bit over time. So we have an image of a flower. Wait, what more?
Yeah. Make the slide mode. Oh, so people can see a little bit better. And also zoom in. Yeah.
Thank you, Jordan.
Yeah. So for those of you who just opened this, but by the way, you can find this demo here on the Backtrack cluster. It should be something called convolution plus pooling demo. And the first thing you do after you open this is go to File and make a copy. So save a copy in Drive, because this is going to be read only for you guys, so you guys can play around with it. But if you make a copy, you'll be able to do so in your own Google Drive. Is that clear? Okay, awesome.
So let's import necessary libraries. Yeah. All right. And right here, we're importing the image that we're going to use today, which is the image of a flower, as you can see. And then right now, you see the dimensions of the image. It's 500 by 500 by 2. So this is a pretty dense image, right? It has thousands upon thousands of pixels across its different channels. And this is the code for a convolutional operation. Right now, you really don't have to understand this code specifically, because there are some complexities to it, but this is how it works, right? So you essentially go to the kernel, and you take a dot product of that kernel, and then you sum that dot product over the different channels of that image. So that's what the convolution operation is. And for time, we'll speed through it. This is the convolutional layer. It's some inner technicalities that we have for this. And
we're doing this in PyTorch. All this is abstracted away. We have done it in NumPy, which doesn't have a convolutional layer built in. Just so that you can kind of like see what's actually happening, and see that it's sort of like for loop, going through everything, adding everything together. But you won't have to implement this like from scratch yourself unless you take like a deep learning course in CLA, for example. PyTorch does all that.
Yeah, it's abstract everything. So these are the different kernels we're going to apply to the image. The first is called an embossed kernel. It essentially gives the image like a 3D field. And the second is an edge detection, outline edge, and diagonal detection. These are kind of like, I think from the name, you can sort of guess what these kernels would bring. They're detecting edges, they're outlining the image, and so on, right? Let's load that in. And now we're going to see how these images affect, how these kernels affect the image. So that's the added size of our image, right? And then you see, this is our first kernel. It's called the embossed kernel. It sort of gives it a 3D feel. Do you guys see it? Wait, you can see it pretty well, right? Yeah, okay. I hope you guys can see it. And this one, it's, what was it again? Yeah, it's the edge detection kernel. And so it detects the edges of that image, right? So in this case, it's detecting the vertical edges of that image. It's reducing the image from all the noise to just the vertical edges. I also want to speak on this one. This one now is looking more on the horizontal edges of the image rather than just the vertical edges, right? And so yeah, this is another kernelized image. And now let's give you an example of the pooling layer. This is the pooling, and this is the pooling layer at the end. So you see, in this case, we're using average pooling. So we take an average of the original image locally, right? So it looks kind of blurred, right? And I remember one person had a really good question on what the effects of average and max pooling were. Let's change this up to max. Let's see if there's a different image. You see, now there's a different image. It's much more sharper and it sort of looks rigid. It's not smooth anymore, right? That's the difference between average and global pooling. And now let's give you guys a brief overview of how an actual convolutional layer works. This is essentially what a convolutional layer is without the gradient effect part. So we're going to put it through a convolution, and then we're going to put it through a pooling, right? And this is going to be the last. Yep. And so here is the final result. Now, this might look a little bit unclear, but for the computer, this is kind of gold, right? So because it gives it all of it, gives it some important information. For example, some of the vertical lines, some of the edges of the image. So this is sort of a reduced version of the image that we had at first. So yeah, that's our demo. And so these are some of the classifications: self-driving cars, facial recognition for social media, and so on.
And also, this Saturday, we have an AI reading group on using diffusion models to predict climate data, which is also a really advanced application of CNNs. If you're interested, come and hear our officers who have been doing research on this. Next.
Also, thank you for your questions, guys. We appreciate the questions. Yeah.
We have ethics stuff we don't have time for today, but we were definitely going to talk about in the future. And yeah, thanks for coming. Here is the attendance code. It's going to be on the platform. We will read it and try to improve our workshops. Right over there, our attendance code, if you want us to birthday points on the panel. Next week, we're going to talk about modern scaling architectures, and we're also going to be going through a demo of actually building a CNN from scratch in iPhone Control. And we're going to see how we will be able to actually implement it out. So, hope to see you there.